Traces explain one bad request, but metrics tell you when the whole LLM service is drifting. Add OpenTelemetry RED metrics in Python for latency, errors, and cost. This is the workflow you'll know how to run when we're done, which logs each language model call and reports latency, errors, and demand for monitoring. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. LLM APIs are noisy in production. One slow call looks like a trace. 10% slower calls across many users looks like a trend. RED metrics give you request rate, errors, and duration, so you can spot drift before users complain or bills spike. Teams who add these signals cut mean time to detect and mean time to resolve by orders of magnitude, because dashboards and alerts see system-level problems, not individual traces. At a high level, RED metrics are simple. Request rate counts calls. Errors measure failed responses divided by total calls. Duration captures how long calls take. Together, they paint the health picture you need for SRE-style alerts and cost monitoring. They're lightweight to collect and much cheaper to export than full trace sampling. We will build a minimal Python pipeline that exposes those three signals from a small batch of sample LLM calls. You will see a meter provider, a counter for calls, a histogram for latency, an observable gauge for error rate, and a cost counter that turns token counts into spend. None of this requires changing your model code deeply, just a few instrumentation hooks. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. To get started, we need a meter provider that tags metrics with service identity and prepares a simple push pipeline for local validation. This snippet sets up an OpenTelemetry meter provider for the LLM gateway resource. The resource object tags every metric with service.name, so downstream dashboards group the signals under the correct deployment. Periodic exporting metric reader paired with ConsoleMetricExporter simulates the push pipeline that a collector or vendor backend will pull in production. The provider becomes global through metrics.setMeterProvider, and metrics.getMeter returns the LLM.RED instrumentation scope that future RED metrics will share. The printed meter scope value confirms the scope name attached to each emitted metric point. With a provider in place, you need a basic request counter so rate and error slices are visible to dashboards. This example uses the LLM.RED meter to count API calls with a synchronous counter instrument. Meter.createCounter names the metric LLM.request.count, so backends can treat it as the RED request rate signal. Call status holds a small batch of successful and failing calls, and the loop adds one per element while attaching route and status attributes that keep error slices visible. Because counters only increase, each add call is safe, even when exports retry. The printed call volume shows how many requests were tallied, confirming that the counter matched the sampled traffic. Counting calls is helpful, but latency is where you catch user pain. Add a histogram to capture per call durations so you can track P95 and P99 trends. This snippet layers an OpenTelemetry histogram to capture latency for the same LLM request cohort. Call latency stores per request durations in milliseconds, and meter create histogram emits LLM.request.latency so collectors can aggregate RED duration stats. The zip loop pairs each latency with its status attribute before latency histogram.record writes the sample, keeping success and failure timings filterable. Latencies sorted then enables a quick local percentile check. mirroring the backend's percentile view. The printed P95 latency messes reports the calculated 95th percentile, showing whether tail delay is drifting beyond expectations. A counter and a histogram still miss a simple signal: the rolling error percentage. That ratio is what triggers many SLO alerts. This code registers an OpenTelemetry ObservableGauge to expose the rolling LLM error rate. Error rate callback counts failed statuses inside call status, divides by the total, and wraps the ratio in an observation tagged with the chat route. Meter.createObservableGauge hooks that callback, so the exporter will pull it each flush, aligning red errors with the same attribute schema as counters and histograms. Invoking the callback locally seeds error rate, letting engineers validate the math without waiting on collector output. The printed error rate confirms that 1/3 of recent calls failed, signaling reliability risk. Finally, start tracking cost so you see spend drift alongside reliability drift. Convert token counts into dollars per call and expose that as another counter. This example adds a cost counter that turns prompt token counts into spend telemetry. Meter.createCounter instantiates LLM.request.cost, while call tokens pairs input and output token totals for each previously recorded request. The loop zips those pairs with statuses, builds the attribute map, computes per call spend using 2 × 10⁻⁶ and 4 × 10⁻⁶ rates, and feeds cost counter. Total cost aggregates the batch spend locally, so operators can reconcile exporter output with billing expectations. Increasing either rate would proportionally raise both the counter and the local sum. The printed total cost USD reveals the precise spend, proving the RED metrics now cover cost drift. This toy pipeline maps cleanly to a real service. In production, you would attach these same instruments inside your request handler. Use an OTLP exporter to send metrics to your backend, and keep the attribute schema consistent across services, so dashboards can roll up by route, deployment, and model version. The small batch here serves as a reproducible example for those same signals. Recap: RED metrics, request rate, errors, and duration give you a service-level view so you can detect drift and spot cost surprises early. Add them when you need quicker detection than traces alone provide. One caveat: metrics show trends but not traces, so keep a sampling strategy for deep debugging. Next step: scale this pipeline by shipping metrics to a collector and adding periodic evaluations of P95 and cost per route, so alerts can trigger on a single signal or correlated conditions. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.